In this video, we'll cover the basics of representing lists as sequences of pairs. So a list in Scheme is just a sequence of elements separated by spaces and enclosed in parentheses, much like this A, B, C, D here. Now, if we want to construct new lists, we can do so by forming sequences of conses together. So I can say cons1 to cons2 to cons3 to the empty list, and the result is the list 1, 2, 3. This extra symbol here, this apostrophe with an empty set of parentheses, represents the empty list, or a list with no elements in it. We'll see why this symbol represents the empty list in the next chapter, but for now, it's just a magical symbol that means a list with no elements. Okay, and it needs to be at the end of these lists in order to create a proper list. But I want to point out as well, there's some pretty printing happening here. We've seen, for example, if I say cons1, 2, it creates a value 1.2. So you might expect with a construct like this cons1, cons2, cons3, we would see something like 1.2.3. Empty list, but instead we see this nice pretty printed 1, 2, 3 list. In essence, when printing out a list, because lists are so prevalent in the list processing language, it gets rid of all these dots. It flattens that one-step nesting of pairs, and it gets rid of or hides this empty list at the end. So all we have to see are the relevant details, just the elements that we see. Everything else is essentially structural and gets hidden when we print out lists in Scheme. But it's worth mentioning that that structure is in fact what we're getting in the background. This box and pointer notation is still relevant, and in fact here's the box and pointer for a similar list to what we constructed here. So the list would be stored in some variable here. That variable refers to a pair, where the first element of the pair is the number 1, so we said cons1, and the second element of that pair is a reference to everything else, so that would be all of this. Okay, and goes on down the list until the very last element doesn't have a reference to something else, just the empty list, acting as a sentinel for the end of the list itself. Okay. Now, if we had to type this out every single time, cons1, cons2, cons3, etc., it would be very exhaustive if we want to create any lists of any reasonable size. So a nice shorthand for creating lists is the word list, and then just the elements that you want to put in there. So list 1, 2, 1, 2, 3 gives us the list 1, 2, 3. So all we have to do is provide just the elements, and it takes care of managing the structure and the empty list at the end. Now, as I said, a list that doesn't end with that empty list is considered an improper list. If we have an empty list at the end of our conses, that creates a proper list. It's the structure that's required. But an improper list is one that doesn't have that. So let's see both of those. If I say define A to be cons1, cons2 to cons3 empty list, so just like what we did before, but now in a variable. And I can say define B to be similar, cons1 to cons2, 3. All conses need to be between two elements, so because we don't have this empty list in our improper list, we just take this 3 and make it the CDR of the last cons there. So otherwise, these two things are pretty much identical. But if we ask what's the value of A, we get the nice looking list 1, 2, 3. We ask what's the value of B, we get 1, 2.3. So the pretty printing doesn't work here because it's not following a natural list structure. We can also ask a few other questions, like, for example, since we can create a list, we can say, is the list 1, 2, 3 equal to A? So A we created out of the conses. So we can ask, is that the same thing as we get if we use the list function? Sure enough, it is. And we can ask, is list 1, 2, 3 equal to the B that we created, this improper list? And it is not. And similarly, we can ask, is A even a list? So there's a predicate for asking, is a value of type list. In this case, A is. And we can ask the same thing about B, and is not considered a proper list. It's just a structure of pairs that doesn't happen to be a proper list, so it's not considered a proper list. So a proper list is important because it means a consistent format in these list structures. So specifically, the car of our list is always going to be an element, so the first element in our list is always pointing to, first element in all these pairs is always pointing to a value. So in this case, it's numbers, but we could also have strings or even other lists. So the car of each one of these pairs points to the element, and the CDR is always going to be a list. It points to the remaining list. So if I ask what's after this, we get a list. If I ask what's after this, we get a list, or the empty list, as the case may be. Okay, so because lists are this linked list structure, lists are essentially references to data, so we need to consider equality of two different sorts. The first being identity comparison, so we want to know are two references pointing to the same exact space in memory. And the other is value comparison. We want to know are two references pointing to two completely separate but functionally identical objects in memory, or possibly the same object in memory. Now, Scheme actually provides a bunch of different ways of determining equality. So there's 4 operations that we'll consider here: the equal symbol, EQ, EQV, and equal, and we'll consider them each in turn. So starting with the equal sign, we've seen this one before. This is how we compare our two numbers the same. So is 3 equal to 4 is false, is 3 equal to 3, that's true. This works specifically only for number types, though. If we say, for example, is list12 equal to list12, we get an error. Contract violation, expected a number, but was given a list, so I can't compare these things this way. Right. One other thing to say about the equal sign before I go to the next one is that the equal sign does do type coercion. So if I ask, is 3 equal to 3.0, that comes up true because it does a widening conversion on this integer, presumably turns them both into floats, and then says, okay, 3.0 does equal 3.0. All right, on to the next one then. So equal symbol does value comparison for numbers only. The EQ symbol here does identity comparison. So this asks, are two things pointing at the same space in memory? So specifically, are two lists referencing the same specific data? So we create two lists here. Define X to be the list 1, 2, 3, 4, and define Y to be the list 1, 2, 3, 4 as well. I'm also going to create another list. Define Z to be an alias to X. So X, Y, Z, they all look the same, but are they? So if we ask EQ X, Y, this comes up false. The reason being, X and Y were both created using this list function, which essentially says create a brand new list in memory, and then on the next line, independently create a brand new list in memory. So two separate spaces in memory, two lists with independent existences. On the other hand, if we ask EQXZ, we get true, because essentially Z here is just an alias for X. So we said take the reference, since X is just a reference to a list, it'd be here pointing at that first element. It says take that reference, copy it into Z, so now we have two things pointing at this same list structure in memory. So if we ask, are they pointing at the same thing, it can very quickly say, yes, it is. All right. Now, one of the issues about this EQ operation, though, is that it doesn't work, or it might not work, rather, for primitive values. It may or may not. It's not guaranteed. It does depend on the implementation itself, and specifically how the implementation interns literal values. The idea here is, well, the way Scheme normally works, if I create two variables, let's call them A and B, and I set them both to the value 2. So I said define A to be 2, define B to be 2. The way Scheme typically works is that instead of creating two separate spaces in memory with the value 2, representing A and B, it'll create one space in memory and store the reference for A and B as pointing to that one space. So A and B will refer to the same 2 in memory. Then if we ever needed to change that variable, if, as we'll later on in the course, have mutable variables, then it could just move that reference rather than having to change the item in that location. Now, that's the way it typically works, but it doesn't always do that. The interpreter is free to store these things however it wants, so we can't assume that two integers or two primitive values will be interred in the same location. So for efficiency or for whatever reason, the interpreter might decide to store these things separately. So for example, I can say EQ, let's just add up two values, 0.2, 0.1, and plus 0.2 and 0.1. So doing this summation, then determining are these things the same, it comes up false. But if I were to say something like EQ 0.3 and 0.3, it comes up true. So these literal values, it does work, but if we have to calculate values and then determine are they equal, it doesn't, which is to say these are not being interred in the same location, they're being calculated separately, whereas somehow these are. All of which is to say, I don't recommend using the EQ operation on primitive values. It's useful if we know we have a reference type like a list and we want to determine are these two lists pointing at the exact same list. But when we're dealing with primitive values, it they don't make sense to have independent or shared existences. It's a good idea to just consider primitive values as values themselves. Try not to think about them in terms of their memory locations. Okay, so we have the equal symbol for comparing numbers. We have EQ for comparing the identity of compound values. The next one is EQV, which is kind of a cross of both, where it works like EQ if we have compound objects passed in, and it works like the equal symbol if we have primitive objects passed in. So, for example, we could say EQV, list 1, 2, and list 1, 2, which we saw for the equal symbol doesn't work. Oh, sorry, those would be two different ones. If we said EQV, two that are the same, like X and Z, though, we'll get true. So it doesn't crash, and it does identity comparison like EQ here. So X and Z are the same. But on the other hand, if I said EQV and then plus 0.2, 0.1, and plus 0.2 and 0.1, so this didn't work for our identity comparison before. But when we're dealing with primitive values like floating point numbers, the value part of EQV kicks in, and it works essentially just like the equal symbol here. Okay, so it does value comparison for primitives and identity comparison for compounds. Sort of a niche thing to need it, because usually speaking, your data is going to be one or the other. If you're in a situation where it might be both, though, this is a good choice to use. Okay, so we got equal, EQ, EQV, and the last one here is equal. So equal question mark. This does value comparison for compound objects. So for example, we asked EQ, X, and Y. Those had different identities, but if we ask equal X and Y, we get true. So they have the same value because X and Y look the same, so functionally they're identical. They're in different locations in memory, but equal essentially goes through each one and says, okay, they have the same number of elements. 1 equals 1, 2 equals 2, 3 equals 3, 4 equals 4. Okay, then they're all the same, so it's true. So it essentially does an element by element deep search through to determine are the structures and the values inside these objects identical. Right, so it also works later on when we have nested lists and all that. So it's a bit of an expensive operation. I recommend using EQ if you just need to determine if two lists are the same list. But if you absolutely need to determine if two independent lists have the same values, this is how you have to do it, using the equal. Now, equal does also work for primitive types. So you can say equal 3 and 3, for example, and that's true. But it doesn't do type coercion, so I can't ask equal 3 and 3.0. That comes up false. It doesn't turn that 3 into a 3.0. It just says, are these things the same? If so, true. If not, false. All right, so those are the 4 different equality operations. And there's one other thing I want to say about equality when dealing with lists, and that is that there is only one empty list. So if I said define A to be the empty list, and define B to be the empty list, so A and B both look like this, I can ask EQ AB, so do they point to the same space in memory? And the answer is true. So all empty lists that you create will all just be referring to this one space in memory. All right, now that we've considered how to construct lists and how to compare lists, now we're ready to consider how to access elements of a list. So we've already seen that lists are constructed out of sequences of conses, so you might rightly assume that in order to access elements of a list, we would use char and CDR. So let's create a list here. We have, actually I can just use, let's redefine X here. Define X to be the list 1, 2, 3, 4, which we saw is the same as saying cons 1 to cons 2, this here. So essentially we created this where the symbol X is at the end of this line, and that points to a pair, which points to another pair, which points to another pair, which points to the final pair. Okay. So since X is pointing just at a pair that's representing the head of a list, if we ask what's the char of X, we should get the first element of that pair. And if we follow our box and pointer, that should give us the element 1. So char of X gives us the element 1. Similarly, if we ask what is the CDR of X, we get the rest of the list. So the CDR of X is everything that's following this pointer, which is the list 2, 3, 4. So it's a smaller list or a sublist. Okay. Now if we want the second element, well, we can see the second element is the first element in the CDR. So what we'd have to do is first take the CDR and then take the char of that. So we'd say so let me type there we go, the car of the CDR of X. And that gives us 2. All right, similarly, if we want the third element, say the car of the CDR of X, that gives us 3, and you can keep adding on to those as you go. Now, if we want, though, we can do this a bit shorter. We can use the convenience methods or the composition functions that say, if we want the second element, for example, we could say the catter of X. The third element, we can say the CDDR of X. If we want the fourth element, CADDDR of X. Notice every time we want the next element, we just CDR down one more time and then take the car. Okay. If we want to take the fifth element, if there were more than 4 elements in this list, we couldn't use these composition operators because they do only exist up to 4 levels deep, but we can continue on in this structure just nesting CDR, CDR, CDR all the way until we get to the point that we want. Okay. Some other useful functions for accessing lists or for working with lists. I believe we already saw this one. There's a list predicate to determine if something is in fact a proper list, and that returns true for X. But for example, list of, let's say the number 3 is false. And there's also the built-in operation for determining is something the empty list. So you can ask, is X the null list? And that's not because X already has values in it, but we can ask similarly, is the empty list null? And that's true. Notice these operations here are identical to asking EQ is something equal to the empty list. Right? That's asking the exact same thing. So is null X asking, does X have the same reference as the only empty list out there? Okay, so that teaches us how to access different elements of a list, or at least how to start accessing elements of a list. Next is consing to a list. That is to say, adding on to the elements of a list. So let's see how that works in the box and pointer diagrams first. So let's draw a simple list here. So list is a pair, another pair, another pair. Let's just do a real simple list here. Oops, did that not give me a line? There we go. Okay, good enough. Where this points to there, and this points to there. This is our dead end, and these will be our values. 1, 2, and 3. 1, 2, 3. Okay, so there's a quick and dirty box and pointer diagram of a list cons 1 to cons 2 to cons 3 empty list. Now, if we wanted to add an element to this list, let's say we wanted to add an element to the front, so we could say something like, this is our list X. We could say cons 0 to the list X. And that gives us the list 0, 1, 2, 3, 4. Notice that doesn't actually change X, it just says return this new pair that where the CDR happens to point to X. So effectively what that's doing is it's creating a new box over here. Oops, I need a box point, okay. So it creates a new box over here where the car points to the value 0 and the CDR points to whatever X pointed to, just there, right? We had our pointer here that said X. So X still refers to that list. That was our original list, but now we've added on this new thing that happens to point to it as well. Okay, so not too bad. Consing to the front of a list is actually quite straightforward. Consing to the end of a list, however, is a bit of a hassle. So if I were to say something like cons X and value 5, let's say, well, that does not look like a list. The reason being, if this is our list here, so 1, 2, and 3, can I copy in this? I don't think I can. So if this is our list 1, 2, and 3, if I'm saying cons X, the value 5, so that's creating a new pair where the car points to X and the CDR points to 5. So I'm creating a new pair here. Oops. Probably could have left myself some more space. Creating a new pair here where the car points to X. So it points to what X points to in this case. And the CDR points to the value 5. So from the box and pointer diagram, it should be very clear that this does not look like a list anymore, right? When we cons to the front, no problem. It cons straight onto the front. The CDR pointed to the previous head, so it's now the second element, where this is our new first element. But if we cons to the back, well, it doesn't work the way you'd expect. It doesn't take the entire list and say replace this with a 5. It says create a new pair where the car points to the previous list and the CDR points to 5. So this is no longer a proper list, in part because it doesn't end with an empty list as it always has to, like in here. And also, it doesn't have the values all in the car slots, right? The 5 is in the CDR slot of this pair. So that doesn't really make any sense. So, which is to say, if we want to extend an existing list, it's real easy to const to the front of a list, but consting to the back of a list is actually kind of hard. We'll see how we can do it in the next video, where we'll have to learn all about the list operations involving recursive processing through these recursive sequences. And I'll see you in that video.